This is the third and final section of the complex numbers chapter, and this is on transformations of the complex plane. So I'm just going to introduce you to, or remind you of the notation that we use. So here we have complex plane, and we'd have some sort of function of z equals something that we plot on this complex plane. And what we've been doing when we want to write that complex number as a Cartesian equation, we want to convert to a Cartesian equation, we would write x as, or z as x plus iy. Now when we do a transformation of z, the normal notation is we say w is going to equal some function of z. So we're doing something to z and we're calling it w. Now this will move the points that we originally started with on this plane onto the same imaginary plane, but now we'll be plotting complex numbers which we'll describe as w, and the notation is that w will equal u plus iv or vi. So this is just the standard notation. This is the plane that we start with, and over here this is the plane that we finish with. It's still a complex plane, but this is the standard notation. So starting plane to the finishing plane over here, and we start with maybe circles or half lines, that type of thing, and they get transformed, maybe they get enlarged, maybe they get translated, maybe they get changed completely onto this plane over here. Now the steps that we need to follow if we want to work out what a transformation does. So we'll start with our z equals whatever we've been given. That needs to be substituted into our w equation, and you'll see some examples like that, so that we'll have some function of w now here, or w equals something, some sort of complex stuff going on here, and then we'll be able to see what a transformation does. So we might even want to plot w on an Argand diagram. Okay, so what transformations do we need to know and what's useful? So let's start with some useful rules first of all that are going to help us go from z or z to w. So we've got rules to do with modulus. If I've got the modulus of a product, it's equal to the product of the moduli. That's useful. We've got when we've got the modulus of a quotient or a division, then we can apply this rule. So we find the modulus of the complex numbers, then we divide. We've also got rules to do with the arguments. So if you've got the argument of z1 times by z2, that's equal to the argument of z1 plus z2. So hopefully you'll remember these rules from core 1. So I'll put a link in the description so you can go back and have a look at those if you need to. And the other rule to do with arguments is if we're dividing the complex numbers, we can find a new argument by subtracting the arguments of z1 and z2. So let's have a look at the transformations. Now if you remember these transformations, if you see them in a question, then you'll know exactly what they do. So if we see a transformation like this, w equals z, so z is the complex number we start with, or the rule that we start with. What this will do is actually this will do a transformation of z. So we'll start with z, that might be a circle, it might be a half line, if you see something like this, then this is a transformation. So it's well, actually it's a transformation, it's a translation, that's what I meant to say. And it's a translation of A, B, whatever these numbers are here, A and B, it will be that type of translation. So not transformation, it's a type of transformation. It's a translation. If we see a transformation like this, W equals KZ, now K is a real number, so it's not a complex number, then this is an enlargement of scale factor K, and the center of that enlargement is going to be the origin. Okay, so if you see something like that, you know it's going to be enlargement. And if you see something like this, W equals IZ, this is actually a rotation. So if you take your equation, you multiply it by I, you end up with a rotation, and it's actually a rotation which is anti-clockwise of pi over 2, so 90 degrees, and the center of rotation is the origin again. So center of rotation is the origin, so 0, 0, or 0 plus 0i. Then the last type of transformation, this one is of the form W equals AZ plus B over CZ plus D, and this is called a Mobius transformation. This is where strange things start happening, where you transform circles and they become lines, things like that. Now here, the A, B, C and D, these can be complex numbers. So not like this one here where K is a real number. A, B, C and D here can be, or are in the set of complex numbers. Okay, so you've got a point P represents the complex number Z on the Argand diagram, where the modulus of Z is 2. So basically this is a circle centered on the origin with radius 2. So I'll just draw that here. Okay, so this is what we're starting with, like this. So 2 minus 2 minus 2, 2. And we've got T1, T2 and T3 represent transformations from the Z planes where x equals x plus iy to the y plane where w equals u plus iv. Describe the locus of the image of P under the transformations. So we're taking this circle, we're applying a transformation, and basically we want to describe what it looks like, so it may be helpful to draw a diagram. So part A, we are applying this transformation. So the steps are, we've got w equals z minus 2 plus 4i. So the first step is going to be to make z the subject of that. So I'll have z equals w plus 2 minus 4i. Now we want to be able to substitute in this the modulus of z equals 2. So we just do the modulus of both sides. So you've got the modulus of z equals the modulus of w plus 2 minus 4i. Then we can substitute this modulus of z for 2. And actually I'll just flip this around. So you've got w plus 2 minus 4i equals modulus 2. And then what I can do, if I just stick some brackets in here and a minus sign, then I know this is going to be the equation of a circle. So it'll be w minus, then in brackets, negative 2 plus 4i equals modulus of 2, which is just 2, isn't it? Okay, so I don't need to change this to a Cartesian equation. I can see this is a circle, so let's just draw it. That will be my description of the image. So this transformation here, T1, is this a translation? The circle moves across so that its center is now at -2, 4. So let's put that here. So 4, -2. The radius of the circle remains the same, so it hasn't got any bigger or any smaller. And I want to draw this so it's touching the right places. If it's got a radius of 2, so I'll go there, there, up to 6, down to 2. So I'll just join those up and mark my axis here. The top at 6, the bottom at 2, there's 0, and there's -4. Now, since this is moving to transformation from this XY plane to this UV plane, we can, when we write the real and imaginary bits here, we could put VU here and we can put V here. Right, okay, let's move on to part B. So in part B, we've got a slightly different transformation. W equals 3Z. So again, I want to get it into a form where I can substitute the modulus of Z equals 2. So I'll start by making W the subject. So I'll have W over 3 equals Z. Now I'll do the modulus of both sides. So I'll have the modulus of W over 3 equals the modulus of Z. I can now replace the modulus of Z with 2. So I'll have the modulus of 3 over W equals 2. Now, what I can do with this now, one of the rules of modulus, I'll put it over here, is that if you've got the modulus of, let's say, A over B, that's equal to the modulus of A over the modulus of B. In the same way, if you have the modulus of A times the modulus of B, that's equal to the modulus of A times the modulus of B. So these rules are useful in sort of dealing with things like this. So this now can be written as the modulus of W over the modulus of 3, which is just 3. Then we times both sides by the modulus of 3, or just 3. And then we'll end up with the modulus of W equals 2 times modulus 3, which is 6. So this is going to be a circle centered on the origin with a radius of 6. So we'll just draw that as our description, or we could actually just describe it in words and say it's a circle centered on the origin, modulus of 6. So we'll have our real here, our imaginary here, and our circle on the origin, radius 6. So 6, 6, -6, -6. So the third one that we have here, we've got this transformation W equals half Z plus I. So same method again, make Z the subject. So then we can get modulus Z and substitute it for 2. So we'll have W minus I equals half Z. We'll times both sides by 2 to get 2. W minus I equals Z. We'll do the modulus of both sides. So that will give us the modulus of 2. W minus I equals the modulus of Z, which we know the modulus of Z is 2. So we end up with this. Then from here, we can use this rule and split this up. We've got a product. So this can be written as the modulus of 2 times the modulus of W minus I equals 2. Then we'll divide both sides by the modulus of 2, which is just 2. So divide both sides by 2, basically you've got w minus I equals 1. So here we've got a circle still, but its radius is now 1. So this transformation has made the circle smaller, and then it's transformed it, it's moved it, or done a translation, and moved its center to I. So I'll just write it in the format that we'll recognize for a circle, which means I need to put the modulus signs in, which I forgot to put in. So that will be w minus, and then that will be 0 plus I, so we can see clearly where the center is. So our description will be our drawing. So you can describe it in words and write down what it is, but it's probably easier to describe it on a diagram. So 0I is where the center of the circle is. It's got a radius of 1, so it goes up to 2, down to 0, and here. And one side will be at 1 and the other side will be at -1. So all we do is join the dots like this, and we've drawn that transformation. Okay, so here for the transformation w equals iz minus 1, find the locus of w when z lies on a half line arg z plus 2 equals pi over 4. So just like in a previous example, we need a way of trying to get these two together. Okay, so I would say the first thing that we'll do, if we've got w equals iz minus 1, is actually to make z the subject of this, then I can put it here where that z is. So I'll just highlight, that's what I'm aiming for. So let's start by making z the subject. So I will add 1 to both sides. So I get this, and then divide both sides by I, and I get z equals w plus 1 over I. Now it's ready to be substituted in to the half line equation over here. So that will give me the arg of, so z gets replaced with w plus 1 over I plus 2 equals pi over 4. Now what I'm going to do, I want to put these together really, because in this form it's not really useful. So I'm going to write the 2 as 2i over I. That way they've both got the same denominator, w plus 1 over I, and then they can go together. So 2 is the same as 2i over I equals pi over 4. Right, what I can do now is that these can go together over the same denominator. So it becomes the argument of w plus 1 plus 2i over I equals pi over 4. Now what have I got here? I've got the argument basically of something over something. I can use this rule. If I've got the argument of z1 over z2, it's equal to the argument of z1 minus the argument of z2. So let's do that. So argument of z1, which is w plus 1 plus 2i minus, because it's divide, the argument of I equals pi over 4. Now what is the argument of I? Well, if we were to draw I on a Argand diagram, that's just here. So that is an argument of pi over 2, 90 degrees. So I can replace this with pi over 2. The argument of I is pi over 2. So let's do that. So I'll have argument now of w plus 1 plus 2i minus, not just pi over 2. So now we can add pi over 2 to both sides. So I have the argument of w plus 1 plus 2i equals, that'd be 3 pi over 4. Now it almost looks like the equation of a half line. We just need to have it in the form w minus something. And then we can see exactly what it is. So that would be the argument of w minus, and then what's in the brackets here, that will be where the half line starts, where we draw a little circle. So that will be minus, so this has to be minus 1 minus 2i. Right, so now I see exactly what it is. So I could sort of describe it, but I'm actually going to draw it. So let me start by drawing the half line we started with. So if I do this as x and y, so this is the real, this is the imaginary plane. So this is z, this is what we started with, and we started with a half line like this. So we'll draw that on. That has, it starts here at minus 2, because this is the same as argument z minus, and that'll be minus 2 plus 0i. So that tells us where the half line starts. And it's an angle of pi over 4, which is 45 degrees. So this is where the half line starts. Okay, let's draw what the transformation w does, and let's draw where this ends up. So this really is our answer here. So u and v, real imaginary. Now this time our half line is here at -1, -2. So we'll have -1 here, -2. So that's where the half line starts. But this time the argument is now 3 pi over 4. I think that's like 135 degrees. So that goes there like this, and it's this here, which is 3 pi over 4. So you can see what's happened is this has been rotated about the origin by pi over 2, 90 degrees, and then it's been followed by a translation actually by -1, 0 to take it down to here. But as long as we draw where that half line has ended up and we've shown it algebraically, that's fine. Alright, on this question here, this is the transformation. So there's our starting point, and that's the plane that we finish with. And what we need to do is to describe the locus of w and give its Cartesian equation when z lies, well, first of all, an equation with this circle. So since we're dealing with complex numbers, the first thing is we're going to write that Cartesian equation of the circle in complex form. So that's a circle centered on your origin. So the modulus of z equals the radius, which is going to be 4. So all we need to work on now is somehow getting this to go into this w equals z squared. Okay, so let's start by writing that down. W equals z squared. So z squared is the same as z times z, or z times z. So z times z. Now what we're going to do, we'll do the modulus of both sides. So you'll have the modulus of z equals, the modulus of w equals the modulus of the product of z. Now we can use that that said, if we have z1 times z2, the modulus of that, that's equal to the modulus of z1 times the modulus of z2. So we can apply that rule, and we'll get the modulus of w equals the modulus of z times by the modulus of z. Now we've got this in a form where we can now substitute this in. So these modulus of z's we can replace with 4. So we'll basically have the modulus of w equals 4 times 4. So the modulus of w equals 16. So we've proved the result here that this is actually a circle with, well, actually we haven't proved it, have we? I've read the question incorrectly. We want to find a Cartesian equation of this, sorry. Okay, so the next step is to find the Cartesian equation. I thought I'd proved it, but no, I've got to read the question properly. Yeah, so find the Cartesian equation of this. So this is basically a circle, center on the origin, with radius 16. Now, when I write the equation of this circle, because we start with x, y, and the z plane, and this is a transformation, I need to write the equation of the circle in terms of u and v. So think about where we just have x and y, we just replace it with u and v, because it's a transformation onto a new plane, it's still a complex plane. So rather than write x squared, we're going to write u squared plus, rather than y squared, v squared equals the radius squared, 16 squared. So we can write it like that. Or we could just write u squared plus v squared equals 16 squared, which is 256. Right, okay, let's have a look at part B. So part B, we need to find the equation of, a Cartesian equation of z when it lies on a line with equation x equals 1. Okay, so the first step is to take the x equals 1 and write it in terms of z. And it'll be z equals, so x is 1, so I'm using this here, so I can get the Cartesian form, 1 plus I y. So it's not just z equals 1, x is fixed, but y can vary, so we still need to put it there. Now, since we've got w equals z squared, and we've now written z as this, we can say w equals basically this squared. So we'll have 1 plus iy times by 1 plus iy. Let's expand the brackets and see what we get. So that'll be 1 plus 2iy plus I squared y squared. So the I squared here will become minus 1. And so I'll have 1 minus y squared, I'm just putting the real terms together, plus 2iy. Now I've just talked about the real terms and the imaginary terms, so I'll just talk about the real term. There's my real term there, and my imaginary term is 2y. Now up here we've said that w equals v plus u plus iv. So from this, we can say that u equals 1 minus y squared and v equals 2y. So this is going to get us to our Cartesian equation. So what we now need to do is to put these two together. So we will carry on up here. Now the v part here, I can write y equals v over 2. So y equals v over 2, so that's a v there, not a u. I can substitute that into this equation, first one, so that will give me u equals 1 minus v over 2 all squared. Now, since our u is like x and our v is like y, really I want to get this in the form where it's y equals something, v equals something, or v squared equals something. Let's see how we go from there. So u, let me take away 1 from both sides, so that would be negative v squared over 4. So I can rearrange that. If I multiply both sides by negative 4, I will get v squared equals 4 minus 4u, multiplying both sides by -4. Right, so there's my Cartesian equation. Now the likelihood is I'll look at that and think, I don't know what that is, I don't recognize what it is. So let's plot a few points, and then maybe we can see if it's a line, a curve, a circle. So this is our u-axis, this is our v-axis, real and imaginary here. And let's plot a few points. So I think the first thing we'll do is we'll say, okay, what happens when we make u equal to 0? So can we find any points along the v-axis? Well, when u equals 0, that will become v squared equals 4, which will mean v will equal plus or minus 2. So that means that 2 and -2, this crosses the axis. Okay, that's 2 points. Well, let's see what happens when we make v equal to 0. So when v is 0, we'll end up here with basically just 4u equals 4. 4u equals 4, which means we'll end up with u equals 1. So that means on the u-axis here, on the real axis, I'll end up with the number 1. Now hopefully that's enough points to plot, and that tells me it's going to look something like this. So it's a parabola where its vertex is at the point 1, 0. So if you end up with something that's a bit unfamiliar, which you don't recognize, just find some points on the coordinate axis, and hopefully that will give you some idea of what shape it's going to be. So here we've got this transformation. T from the Z plane to the W plane is given by this. So this is an example of what we call a Mobius transformation. So I'll just write that down. So Mobius transformation. And what we need to do in part A is show that the image under T of the circle, so this is what we're starting with, in the Z plane is a line in the W plane. So what we want to show is when we start with a circle and we apply this transformation, what we end up is with a line in the W plane. We're probably going to want to work out the equation of that line, or at least be able to sketch it on our Eye-Going diagram in part B. So let's start with the transformation that we've been given, which is this. Now the first thing that we need to do, we want to rearrange to make Z the subject, and in fact we want to rearrange it so that we get modulus of Z. So rearrange this so we can write modulus of Z, and then we can replace the modulus of Z with 1. Okay, so step number 1, we'll multiply both sides by Z plus 1. So we'll have this. Step number 2, we will multiply out the brackets, so we'll have WZ plus W equals 5IZ plus I. We'll bring the Z terms to one side because we want to make Z the subject. So we'll have WZ minus 5IZ, and then we'll take the W across, so we end up with I minus W. The next step is going to be to factorize out the Z, so we'll have Z, and then in brackets we'll have W minus 5I, like this, equals I minus W. And then the last step will be, we can write Z, well it's not really the last step, but we've got Z as the subject, would be Z equals I minus W all over W minus 5I. Okay, the next step now will be to do modulus of both sides. So we'll have modulus of Z equals then the modulus of this, I minus W over W minus 5I. Now here we can make the substitution and we can replace this modulus of Z with 1. So let's write now the modulus of I minus W over W minus 5I equals 1. Now we want to rearrange this so it looks like some sort of loci that we recognize. So the first thing we're going to do is to use the rule for modulus, and that rule is this: if you've got the modulus of a division like this, you can change it to the modulus of the top divided by the modulus of the bottom. So we'll use that rule, and then we'll have I minus W, modulus of that, over the modulus of W minus 5I. That equals 1. So we can multiply both sides by the denominator. So we'll have I minus W in modulus equals W minus 5I in modulus. Now this is looking a bit like the perpendicular bisector, but this is the wrong way around. Now there is another little modulus rule we can use, and it's understanding what modulus means. So modulus means like the distance or the difference between these values here, the size of the difference between those two. And actually, if let's just write down a little rule over here. If I wanted to find the difference or the modulus of A minus B, it's equal to the modulus of B minus A. So that's another rule that we can use. Here's an example. So if I had the modulus of 9 minus 5, that is equal to the modulus of 5 minus 9. Because here I will get 4, here I'll get negative 4, but it will become 4 on both sides once we do the modulus. So we can apply that rule, and that will allow us to spin this around. Okay, so that will be now the modulus of W minus I, it's the same as the modulus of I minus W, equals the modulus of W minus 5I. Now I recognize that this is like the perpendicular bisector of a line between, well, this is going to be W1 and W2, so we can write that as W minus, and then we'll put 0 plus I. So I'm just writing it out fully so we can see exactly what it is, and then W minus, so here's like my Z2 or W2 at 0 plus 5A. So what I have, which I can now do in part B, is going to be a line like this. So this is going to be U, this is going to be V here. So we want to draw a line that's the perpendicular bisector between the point I, which is here, and the point 5I, which is here. So that's going to be a line that passes through 3I, and that's going to be this line here, like this. Now I'll just straighten out my axis a bit, it's not very straight at all. Let's try again. And we don't need to, but we could write down the equation of this line here, which is going to be V equals 3. So on this question here, we have another Mobius transformation that is transforming this circle in the Z plane, actually, and it tells us to a circle in the W plane. So we know we're going to finish with a circle, and what we need to do is to state the center and radius of that circle, which means we really need to know what is the Cartesian equation. So at some point I will need to replace W with U plus IV and use what I've learned before to work out what the equation of the circle is. Right, so step number 1, let's write down what the transformation is. Now we have this circle which is centered on the origin and has a radius of 2. That's what that means. So center 0, 0 and radius 2. So if we write down what the complex equation is for that, it's the modulus of Z equals 2. So like the previous one, we're going to rearrange this to make Z the subject, then do the modulus of both sides. We've got the modulus of Z equals something in terms of W, then we can make this substitution here. Okay, so let's do that. So multiply both sides by Z plus 1, the denominator, and then we've got 3Z minus 2 on the other side. We'll expand the brackets, so we have WZ plus W equals 3Z minus 2. Then we'll bring all the Z terms to one side, so we'll have WZ minus 3Z equals minus w minus 2. Next step from this is we'll factorize out the z. So I have z, and then here we will have w minus 3 equals minus w minus 2. Then we'll divide both sides by w minus 3. So we end up with this. Z equals minus w minus 2 over w minus 3. Next step is to do modulus of both sides. We'll have the modulus of z equals the modulus of all of this, minus w minus 3 over, sorry, minus w minus 2 over w minus 3. Now we can make the substitution and replace this modulus of z with 2 here. So that now becomes the modulus of minus w minus 2 over w minus 3 equals 2. Right, okay, so what do we do from here? Well, we want to multiply both sides by this denominator here, so we'll split up the modulus like this using that rule for division, and modulus like this. So we've got the modulus of top, modulus of the bottom equals 2. We'll multiply both sides by the denominator, so we'll have the modulus of negative w minus 2 equals 2 times modulus w minus 3, like this. Now, this looks a bit problematic. I don't really want to have like this negative w minus 2. Is there anything I can do with that? Well, yes, I can. Right, it actually becomes, and I'll show you why in a moment, it becomes the modulus of w plus 2 on this side equals 2 times the modulus of w minus 3. Now, why does that happen? Well, basically what we're saying is what's the difference? What's the size? What's the absolute value between negative w and negative 2? Well, it's exactly the same size or absolute value or distance as it is from those two. Now, why is that? If we want to prove it algebraically, we could say that we could take a negative 1 outside and say this is the same as negative 1 times by w plus 2 and a modulus of that. Then we can use our rule for products and modulus and split them up like this. Now the first bit here where we've got the modulus of negative 1, well, that's just 1. So this just becomes the modulus of w plus 2. Okay, so that's why we end up with this here. It means the same thing. Right, so we may recognize this here as like z minus z1 equals k times by z minus z2, and here we have like w. So we know this is going to be the equation of a circle. So we need to do this algebraically. Now we've done things like this before. So what we need to do first of all is replace the w with u plus iv. It's got u plus iv plus 2. So that's like w plus 2 equals 2. And then we'll have u plus iv minus 3. This is because we want to find a Cartesian equation. The next thing I'm going to do is to group together the real and imaginary terms. So in the left hand side I'll have u plus 2, that's the real term, plus, and then v is the imaginary term, I. I'll do the same on the other side, so I'll have 2. That's outside of the modulus, so let's just put the modulus in the right place. So 2 modulus, so this will be u minus 3, that is the real term, plus, and the imaginary term is v, like this. Now the reason we've done that is because we are going to square both sides, and when we square both sides, that gets rid of the modulus. By squaring both sides, we're saying what's the distance squared? Okay, and the distance squared is going to be the real part squared plus the imaginary part squared. So what we end up with next will be u plus 2 all squared plus the real parts, imaginary part squared, sorry, which is going to be v squared, equals, now we need to square the 2, so it becomes 4, times by u minus 3 squared plus v squared, like this. So the rest is algebra, so we need to be really careful with what we do after this, because we could easily slip up with signs or simple numerical errors. So we've got to be really careful expanding this out. So let's expand first of all the u plus 2 all squared. So that becomes u squared plus 4u plus 4 plus v squared. So there's the left hand side. Then on the right hand side, I'll have 4 times by the u minus 3 all squared becomes u squared minus 6u plus 9 plus v squared. So what we'll do now is we'll multiply this out by 4 and see what we get. So that will be u squared plus 4u plus 4 plus v squared equals, so we'll have 4u squared minus 24u plus 36 plus 4v squared. Next step is going to be to collect together the terms. So I can see, right, I've got 4u squared, take away u squared, so that'll be 3u squared. If I'm basically bringing everything to this side. What else have I got? I've got negative 24u minus another 4u will be negative 28u. Then I'm going to keep the numbers all together because I know it's the equation of a circle. I'm going to keep the numbers on the other side because I know I'm going to have to move them at some point. So I'm going to do that now just to make things a bit easier. Then we have a look at our v squared. So I've got u squared. I've got 4u squared. Take away a v squared, which will be plus v squared, 3v squared. Now if I keep the numbers separate, I've already got the 4 that will be on the other side, and I need to take away 36 from both sides. So 4 minus 36 is going to be negative 32. The next step now is going to be to complete the square on these two things here. Oh, before we do that, we need to divide both sides by 3. So I'll put divide by 3. So I'll have u squared minus 28 over 3u. So when you do these questions, if you don't get whole numbers, don't panic. That can sometimes happen. Don't think, all right, this doesn't divide by 3 or the 32 doesn't divide by 3. I've done something wrong. Okay. In this case, we're doing it right so far. So plus 3 squared equals negative 32 over 3. Right, so let's complete the square. So this will be in brackets u minus half of 28 over 3 is 14 over 3 all squared. So I need to subtract a 14 over 3 all squared for this to balance. Don't really need to, or I don't need to complete the square on the v squared. That's just as it is, equals negative 32 over 3. So now I'm going to add 14 over 3 squared to both sides. Now I think 14 squared is 296. So I need to add 296 over 9 to both sides. So if I do that, I will have u minus 14 over 3 all squared plus v squared equals 100 over 9. Okay, and that sort of seems to be quite nice, doesn't it? Because then the radius is going to be the square root of that, so it's going to be 10 over 3. So even though we got some odd numbers, we got the radius worked out nicely on the left hand side there. So we're ready to write our final answer. Sorry, not left hand side, right hand side. So the center of this circle is going to be at 14 over 3, not negative 14 over 3. 14 over 3 is 0. So write that in, 14 over 3, 0. And the radius, well, that's just going to be the square root of this, which is what we said was 10 over 3. So there's a lot of algebra in this question. So you really need to take care when you're multiplying things out, moving terms from one side to the other, because if you're not careful, you can make a little algebraic slip and end up with the wrong answer. So do take care on these questions. Okay, so we've got a transformation T of the Z plane to the W plane is given by this, another Mobius transformation. Show that as Z lies on the real axis in the Z plane, then W lies on a line L in the W plane. Sketch L on an arcane diagram. Now in this one, it doesn't give us the equation. It doesn't give us like z is a circle or anything like that. It just says it lies on the real axis. Now, one way to approach this would be to say, okay, let's draw a little Argand diagram here, like this, and this is x, and this is y, and the line we're talking about is this line here. Yeah. Now you could say that this is this z minus or z plus I equals a modulus of z minus I. Okay, so basically you're saying it right, it's the perpendicular bisector of those 2 points. That's quite complicated. And to try and rearrange this to make z the subject and try and substitute this in is going to be quite tricky. Another way of thinking of this is that if z lies on the real axis, which is this blue line here, it means that the imaginary part of z equals 0. So we'll write that down. Since z lies on the real axis, the imaginary part of z equals 0. And that's what we're going to use to help us with this question. Okay, so we haven't got an equation as such. What we know is the imaginary part of z is 0. So let's start with our transformation. And the first few steps are all the same as what we've done before. So rearrange it to make z the subject. So we'll have w and then 1 minus z equals iz minus 2. Expand the brackets. Wz or w minus wz equals iz minus 2. Put the z terms on the same side. So we'll have iz, minus or negative wz minus iz equals negative w minus 2. Let's multiply everything by negative 1 to get rid of the minuses. So we'll have wz minus or plus iz equals w plus 2. Let's factorize it. So we'll have z and then in brackets w plus I equals w plus 2, and then we can say, right, that z equals w plus 2 over w plus I. Now what we're going to do now is replace w with u plus v, because basically what we want to do, or u plus iv, basically what we want to do is get to a point where we can say, right, okay, what's the real part of all of this? What's the imaginary part of all of this? And then we can use that to say, right, we'll equate the imaginary part of all of this to 0. So yeah, z equals, so the first w gets replaced with u plus iv plus 2 over u plus iv plus I, u plus iv plus I. Now we want to get rid of this fraction here, so the way we're going to do it is to multiply the top and the bottom of this by the conjugate of the bottom. In other words, we probably need to put the real and imaginary parts together first before we do that. So I'll have z equals, and we'll probably do the same with the top. So real part u plus 2 plus iv, and then at the bottom real part is just u, and then the imaginary part is going to be v plus 1 I. So we're going to multiply the top and the bottom of this fraction by u minus u plus 1i, the conjugate of this, to almost like rationalize it in the complex way. So let me write down times by u minus v plus 1i over u minus v plus 1i. Now the actual bottom part of this we can work out quite easily. That's going to be the sum of two squares. So that's just going to be u squared plus v plus 1 squared. So u squared plus v plus 1 squared. So we'll just do that the quick way. So if you're not sure about that, have a look back at the complex numbers from core 1 about how we can quickly do this type of calculation. We don't want to multiply it out. And the top has a lot of multiplying out. Now we're not going to multiply out all of the terms, because actually what we're interested in is looking at what is the imaginary part of what we have of all of this. So we'll write the terms down, but we may not necessarily multiply them out. So here, when we've got u times by u plus 2, I'm just going to write that as u times by u plus 2. Then the next bit is going to be this u plus 2 times by this, and it's going to be a minus. So I'll put minus, and this will be u plus 2, and that will get times by v plus 1 I. Then it's going to be these two multiply together, so that'll be uvi, so plus uvi, and then the last multiplication is going to be this iv times by this here, so it's going to be, make that a bit longer, minus v times by v plus 1, and because we're going to have I times I, so we're going to have I squared there. Now, as I said before, I'm interested in the imaginary parts equaling 0. So that's going to be this here and this here. So before I actually go on and sort of write down like the imaginary part equals 0, I'm just going to rearrange it so that I see the real part, which is going to be this. So I didn't need to multiply out the brackets. And also the last term, because it's going to become plus v times by v plus 1. So all of that's the real part. Now my imaginary part is going to be these two terms here. So I'll put those in brackets. So plus, let's write uv minus u plus 2 times by v plus 1. All of that is I, and that's all over this denominator. So my fraction line there, not completely straight, but hopefully we get the idea. Right, so now we can draw on this statement at the top. Since z lies on the real axis, the imaginary part of z, which is this bit here, equals 0. So let me just highlight that. We've put it all together. So this equals 0. So I can go on and write that statement because I've already stated at the start that the original imaginary part of z equals 0. So I'll have uv minus u plus 2 v plus 1 equals 0, and the rest is about finding out what this actually is. Right, so we'll expand the bracket, so we'll have uv minus uv, okay, that's handy, plus u plus 2v plus 2 equals 0. Now you can see that these two terms are going to cancel out, so that just leaves u plus 2v plus 2 equals 0. Now I've just realized actually I've made a mistake here. I forgot about the minus sign. So all of these terms here are going to be minus. So it should be negative vu, negative u. They're all going to be negative. So I'll just rub those out and put the negatives in. There we go. That means actually that this is going to be slightly different, isn't it? So it will be, these are all going to be negatives. Negative u minus 2v minus 2 equals 0. So I think that's right now. Now, when we're in the z plane, our Cartesian equation is going to be y equals some function of x. Okay, that's in the z plane. When we are in the w plane, then what we will have is v equals some function of u. So we want to write this in that form. So basically it's going to be v equals something in terms of u. So I could write 2v equals, so that will give me negative u minus 2. Then divide both sides by 2 and I'll get v, so that's a bit like y, equals minus a half u minus 1. So this is our Cartesian equation in the W plane. So I can finish this off now by drawing an Argand diagram as required. This shouldn't be too difficult because it's just a straight line. So it's a straight line that's going to be crossing the v-axis at -1. So I'll just put -1 here. And it's got a negative gradient. So it's going to be a line that sort of goes down this way like that. And that's meant to be a straight line. So I'll try that again. So a line that's going like this. That's a little bit better. And it would be useful, we don't need to, but it would be useful to write down what this coordinate here is. So this coordinate here will be when v is 0. Okay, so maybe I will just do this. That point there is when v is 0, which means that negative a half u equals 1. And then from there, timesing both sides by -2 will get u equals -2. So we'll just show off and write that coordinate down there as -2. So I'll just highlight our answer here, and well, this is our answer here really, is this Argand diagram which we've drawn at the bottom. So you should now be able to do exercise 3C on pages 107 to 109. So we'll start with a quick recap, looking at the different types of transformations. So when we have a transformation like this, plus IB or BI, this is a translation of the form AB, and A and B we can just get from here, these two values. So if we recognize that, we can go ahead and just state it's a translation. We have enlargement, so if we see a transformation like this, that's an enlargement. By the way, K can be any real number, so it's not a complex number, it's just a real number there. So it's enlargement, and the center of enlargement is the origin, 0, 0, and the scale factor of enlargement is equal to K. Then we have W equals IZ as a transformation, and this is a anti-clockwise rotation, about the origin, and the center of rotation, I'll just put C of R, is actually I've said what the center of rotation is. I meant the angle of rotation, so rotation about the origin, and its rotation angle equals pi over 2, so it's like 90-degree rotation about the origin going back that way. Okay, and then we have these Mobius transformations, and those will be of the form W equals AZ plus B over CZ plus D, and here the values of A, B, C and D, well, these can be complex values, not real values like the enlargement. So in all of these types of questions, we start with the Z plane, which we label as X and Y. We have this transformation, and it can be one of these 4 transformations up here, and it does a transformation to the W plane, which we label as U and V. And pretty much in most of these questions, the approach that we're going to take is that we'll rearrange the transformation into the form Z equals something, so we'll make Z the subject. Let's write this down. Make Z the subject. After we've made Z the subject, the second step is going to take the equation of Z that we've been given and substitute it into this equation here that we've made Z the subject of. So step 2 would be substitute, and the rest is all algebraic to find out either what the Cartesian equation is of our transformed line or circle, whatever it is, or it may be a complex equation that we recognize. So for example, like the circles, we would recognize if it's in that form. It may be the perpendicular bisectors like this. And if we end up with something in this form, there we've got K there, it looks like the perpendicular bisector. This one will be a circle, but remember K is not equal to 1, and K will be greater than 0.